In this lesson, we will look at radioactive decay and an application. Radioactive decay. The amount of a radioactive element A at time t is given by the formula A of t equals A naught times e raised to the power kt, where A of 0 equals A naught is the initial amount of the element and k is less than 0. Note the similarity to A of t equals P times e raised to the power RT, where we were referring to an amount of money, and N of t equals N naught times e raised to the power KT, where we were referring to a number of organisms. An example: iodine-131 is a commonly used radioactive isotope used to help detect how well the thyroid is functioning. The half-life of iodine-131 is approximately 8 days. If 6 grams of iodine-131 is present initially, how much will be present 2 weeks later or 14 days? We will convert everything to days here to make things simpler. The half-life, something we need to know. The half-life is the time required for half of a radioactive substance to decay. The solution to our problem, step 1, is to determine K using the half-life. The half-life here is approximately 8 days. I will use my formula A equals A naught times e raised to the power KT, and note that at the half-life of 8 days, the amount that we have is going to be equal to 1/2 the amount we started with. So A is going to equal 1/2 A naught. I'll plug in 8 for T. And I have 1/2 A naught equals A naught times e raised to the k times 8. I will divide through by A naught, giving me 1/2 equals e raised to the power 8k. Take the natural log of both sides. The natural log of e raised to the power 8k is 8k. So I have the natural log of 1/2 equals 8k. By dividing through by 8, I have found that k is equal to the natural log of 0.5 divided by 8. Okay, so next, step 2. If 6 grams of iodine-131 is present initially, how much will be present 2 weeks or 14 days later? Okay, we use A equals A naught times e raised to the power KT. We remember that k is equal to the natural log of 0.5 over 8. And here I will plug in 6 grams for A naught, the amount we start with, and I will plug in 14 days for T. So I have A equals 6 times e raised to the k times 14. Plugging this into a calculator, A is approximately equal to 1.784. So the solution is that there will be approximately 1.784 grams of iodine-131 present 2 weeks later. Okay, another question. How long will it take for 90% of the initial amount of iodine-131 to decay? We'll use the same formula, A equals A naught times e raised to the power KT. And if we think about it, when 90% of the initial amount has decayed, the amount we're left with is 10% of what we started with. So A is equal to 10% of A naught. So I will replace A with 0.1 A naught in the formula. I know what K is. I'll divide through by A sub 0, and I will have 0.1 equals e raised to the power KT. Take the natural log of each side, giving me the natural log of 0.1 equals the natural log of e raised to the power KT. The natural log of e raised to the power KT is KT. So I have the natural log of 0.1 equals KT. If I divide through by K, I have T is equal to the natural log of 0.1 over K, and I know what K is, so I can plug this into a calculator and find that T is approximately equal to 26.6, or approximately 27 days is the time for 90% of the initial amount of iodine-131 to decay. Try on your own. Radium-221 has a half-life of 30 seconds. How long will it take for 99% of a sample of radium-221 to decay?